Welcome. Settle in. Let your body grow heavy against whatever is holding you right now, and allow the world outside to fade just a little. Tonight, we're going to wander together through the questions that science has not yet answered. Not the solved ones, not the theories confirmed in laboratories, or the facts written in textbooks, but the open ones, the quiet ones, the mysteries that remain at the edges of human understanding, waiting patiently, like stars just beyond the reach of our telescopes. For every mountain science has climbed, there is another range waiting on the horizon. And that is not a failure. That is the most beautiful thing about knowledge, it keeps opening. Every answer reveals a deeper question. Every discovery parts a curtain, and behind it stands something stranger and more wonderful than what came before. So let these questions be gentle company tonight. You don't need to solve them. You only need to let them drift through your mind, like leaves carried by a slow river, while your breathing slows and sleep draws nearer. If the Sleepy Science channel brings you comfort, consider sharing it with someone who might need rest. But for now, let's begin. Why is there something rather than nothing? Let us start at the very beginning. Not the beginning of Earth, or the beginning of life, or even the beginning of our universe, but the beginning of everything. Or rather, the question that sits before the beginning. Why does anything exist at all? Sounds almost too simple to be a real question. And yet no scientist, no philosopher, no poet has ever answered it to everyone's satisfaction. Physics can describe how the universe behaves once it's already here. Cosmology can trace events backward to the first fractions of a second after the Big Bang. But why there is a universe to describe, why there are laws of physics, why there is space and time at all remains completely open. Quantum mechanics offers a curious clue. Even the emptiest regions of space are not truly empty. They hum with fleeting activity, with particles flickering briefly in and out of existence. Some physicists suggest the universe itself may have arisen in a similar way, that absolute nothingness is somehow unstable, that something is always destined to emerge. Others imagine our universe as just one bubble among an endless sea of bubbles, each a separate universe with its own physics, its own history. But even that only pushes the mystery back. If a multiverse exists, why does the multiverse exist? Some philosophers have argued that existence is simply the natural state of things, that non-existence is what is truly impossible. Perhaps reality, in some form, has no choice but to be. We cannot test this. No instrument can measure the reason for being, and so the deepest question of all, why there is something instead of nothing, remains open. Beneath every star you've ever seen, beneath every atom in your body, beneath every law of nature, lies this single unanswered question. And it rests there quietly tonight, along with everything else we don't yet know. What caused the Big Bang? We can trace the story of the universe backward nearly 14 billion years. We can describe what it looked like when it was a hot, dense fireball filling all of space. We can chart its growth, measure its afterglow, and study the ripples it left behind. But the moment of its actual beginning, the cause of the Big Bang itself, remains hidden. Some theories describe the universe as a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time in the same instant. Others suggest the Big Bang was not a beginning at all, but one moment in an endless cycle, universes expanding, collapsing, and beginning again in a great cosmic rhythm. What complicates things further is the nature of time itself. If time was born in the Big Bang, then asking what came before may not be a meaningful question. There may be no before. The universe may simply have arrived, the way a dream arrives without cause, without precondition, complete. And yet that answer satisfies no one. Something set the cosmos in motion, something lit the fuse. That true first cause remains one of the most profound and enduring mysteries in all of science. Why does time only flow forward? Think of something broken, a shattered window, a spilled glass of water, a fire that has burned out. These things do not reassemble themselves. Time, in our experience, only moves in one direction, from past to future, from order into disorder, from cause to effect. We call this the arrow of time. What makes this strange is that the fundamental laws of physics don't actually require it. At the level of individual particles, the equations work equally well in both directions. An electron can move forward in time or backward, and the mathematics doesn't complain. Nothing in the equations insists that time should only advance. And yet, the universe clearly has a direction. We remember the past but not the future. Heat flows from warm things to cold ones, and never the reverse. Entropy, the universe's tendency toward disorder, increases, always. Many scientists link time's arrow to this rise in entropy. The universe was born in an exceptionally ordered state, and has been winding down ever since. But that only raises another question. Why was it so ordered at the beginning? Why should the cosmos have started in a condition that allowed time to have a direction at all? Some think time's arrow is connected to information the way knowledge about events spreads and becomes irreversible. Others tie it to the expansion of the universe itself. But no explanation is complete. Time flows forward every second of your life, and no one, not yet, truly knows why. What is dark matter? When astronomers look at galaxies, they see something that shouldn't make sense. The stars at the outer edges of galaxies spin far too quickly. Into the laws of gravity, they should drift away like water off a spinning wheel. Instead, they hold on, orbiting as though some invisible mass is gripping them in place. That invisible mass is what we call dark matter. It doesn't glow, it doesn't absorb light. Telescopes of every kind pass right through it, and yet its gravity shapes everything around it, bending the paths of starlight, holding galaxies together, leaving patterns in the great web of the cosmos. Scientists have searched for decades to find what dark matter actually is. Some think it consists of undiscovered particles, perhaps WIMP, which stands for weakly interacting massive particles, or actions, ghostly particles that barely interact with anything at all. Others suggest it might be ancient black holes, formed in the earliest moments after the Big Bang. Detectors buried deep underground listen patiently for the rare collision of a dark matter particle with an ordinary atom. So far, silence. Whatever dark matter is. It makes up about 5 times more of the universe than everything we can see, every star, every planet, every cloud of gas combined. It holds the universe together, and we don't know what it is. What is dark energy? In the 1990s, astronomers studying distant exploding stars expected to find the universe slowing down. Gravity should be pulling everything back together, like a ball thrown upward that eventually falls. Instead, they found the opposite. The universe is expanding faster and, faster. Something is accelerating its growth, pushing galaxies apart at ever-increasing speed. That something is called dark energy. It makes up roughly 70% of the total contents of the cosmos. It is, in a very real sense, most of what the universe is made of. And we have no idea what it actually is. One possibility is that dark energy is simply a property of empty space, a constant energy that the vacuum of the universe carries within itself. Another is that it represents a dynamic field, something that changes over time, that may have been different in the past, and could be different in the future. This matters enormously because the fate of the universe depends on it. If dark energy remains constant, the universe will expand forever, growing colder and emptier with every passing eon. If it grows stronger, it could one day tear apart galaxies, then stars, then planets, and ultimately even atoms themselves, a scenario called the Big Rip. We can measure dark energy's effects, but its true nature, what it is, where it comes from, what it will do, remains unknown. Why are the laws of physics fine-tuned for life? Imagine turning a dial on the strength of gravity, not by much, just a fraction of a percent. Stars might collapse too quickly to allow planets to form, or they might never ignite at all. Turn another dial, the force that holds atoms together, and chemistry as we know it ceases to exist. Molecules cannot form. Life becomes impossible. This is what physicists call the fine-tuning problem. The constants of nature, gravity, electromagnetism, the nuclear forces appear to be set at precisely the values needed for stars, planets, atoms, and life to exist. Change any of them by even a small amount, and the universe becomes sterile. Why should this be? There is no obvious physical reason why gravity should have the strength it has, or why the electromagnetic force should be exactly as it is. And yet, if they were even slightly different, we would not be here to notice. Some say this is simply fortunate coincidence. Others propose the multiverse, that countless universes exist with varying laws, and we naturally find ourselves in the rare one where the numbers work out for life. Still others believe a deeper principle, yet undiscovered, must force the constants to these exact values. For now, when we look at the night sky and notice that it holds stars, that those stars hold planets, and that we are here to look, we are looking at a mystery. An improbably, precisely tuned mystery. Does the universe go on forever? The observable universe stretches about 90 billion light-years across, but that's only as far as light has had time to travel since the Big Bang. Beyond that boundary, space continues, we just can't see it. The question is, does it go on forever, or does it eventually end? One possibility is that the universe is infinite, that space extends endlessly in every direction, containing an unlimited number of galaxies, stars, and perhaps other worlds like ours. If so, then somewhere unimaginably far away, there may be a world very similar to this one, with someone very similar to you, resting in the quiet, just as you are now. Another possibility is that the universe is finite, but has no edge like the surface of a sphere. Travel far enough in one direction, and you might eventually return to your starting point. Scientists search for clues in the faint afterglow of the Big Bang, into the cosmic microwave background, looking for patterns that might reveal the universe's shape. So far, the universe appears very close to flat. But flatness doesn't settle whether it's infinite. The true size and shape of the universe remain hidden just beyond the horizon of what we can ever see. What lies beyond our cosmic horizon? Beyond the edge of the observable universe, space continues. But it is a place we can never reach, never see, and never receive messages from. Not because there is a wall, but because the universe simply hasn't existed long enough for light from those regions to find us. What's out there? Perhaps more of the same galaxies, stars, planets, stretching on. Perhaps conditions radically different from ours. Some theories of cosmic inflation, the rapid expansion thought to have occurred right after Big Bang, suggest our observable universe is just one small patch in a much vaster reality. Other patches might have formed under different conditions, with into slightly different physics. We are bound within a cosmic island. The sky we see is only the tiniest fragment of what may exist. The rest of the universe is out there, unreachable, silent, a permanent unknown like the dark water beyond the light of a lantern. Does a multiverse exist? Some of the boldest thinking in modern physics suggests our universe is not the only one, that it is one of countless universes. Perhaps infinitely many, each with its own laws, its own history, its own geometry. Some may have more dimensions. Some may have different forces. Some may contain no stars, no atoms, nothing we would recognize. This idea, the multiverse, arises naturally in several theories. Cosmic inflation may have created multiple bubble universes, each budding off from a larger reality. String theory suggests an enormous landscape of possible physical laws, with each universe occupying a different point in that landscape. The concept is intellectually thrilling, but it faces a fundamental challenge. If other universes lie beyond our cosmic horizon, no signal can ever reach us from them. We may never be able to confirm they exist, and a theory that cannot be tested sits at the edge of what we usually call science. Still, the possibility that reality is larger than our universe, perhaps unimaginably larger, is one of the most captivating questions in modern physics. What is space and time, at the deepest level? Einstein showed us that space and time are not a fixed stage, they are flexible, dynamic. They bend under the weight of mass. They stretch near sources of gravity. Time runs slower near a heavy planet and faster in open space. Space and time are woven together into a single fabric called space-time. But what is that fabric made of? At the smallest scales, the smooth space-time of Einstein clashes with the fuzzy, probabilistic world of quantum mechanics. In relativity, everything is continuous and smooth. In quantum theory, everything comes into discrete chunks. These two pictures cannot both be right at the deepest level, and yet both describe their respective domains with uncanny precision. Some physicists believe that space-time is not fundamental, that it emerges from something even deeper, or perhaps networks of quantum information, or the entanglement of particles woven together into geometry. In this picture, what we experience as space and time are surface phenomena, like the ripples on a pond that arise from movements far below. Others wonder whether time itself is real, or whether it is a kind of illusion generated by deeper processes. The stage on which everything happens may not be what it seems. And what it truly is, remains one of the most profound open questions in all of science. Why can a particle be in two places at once? Quantum mechanics reveals something about the universe that no amount of familiarity quite makes comfortable. A particle, an electron, a photon, does not have a definite position until it is measured. Before measurement, it exists in a superposition, a kind of blurred state spread across multiple possibilities simultaneously. This is not a limitation of our instruments. It appears to be a genuine feature of reality. Particles pass through two openings at once, interfering with themselves like waves on water. Only when we observe them do they seem to settle into a single location. What does this mean? Does the particle truly exist in multiple places at once, or is superposition simply a reflection of our ignorance, a description of possibilities rather than realities? Some interpretations of quantum mechanics say that every possibility actually happens, branching into parallel worlds. Others say reality is genuinely fuzzy until observation forces it to solidify. None of these interpretations have been proven. What has been proven is the effect itself strange, reliable, and still deeply mysterious. What is entanglement? When two particles become entangled, something remarkable occurs. Measure a property of one, and you instantly know the corresponding property of the other, no matter how far apart they are. Separate them by a kilometer, or a light year, and the connection persists. When one is measured, the other seems to respond, instantaneously, as if distance doesn't exist between them. Einstein found this deeply troubling. He called it spooky action at a distance, and he believed there had to be a hidden explanation, that the particles must carry some pre-existing information we simply hadn't discovered yet. But decades of experiments have proven that entanglement is real, and that no hidden variables of the simple kind Einstein imagined are responsible. The universe truly is connected in ways that seem to transcend space. What does this tell us about reality? Some physicists believe it suggests the universe is fundamentally non-local, that separation in space is, at some level, less real than it appears. Others think entanglement may point toward information as the bedrock of reality. We use entanglement in quantum computing and cryptography. But why it works, what it reveals about the nature of space and connection, remains an open mystery. Why does gravity feel so weak? Consider a small magnet stuck to a refrigerator door. It is holding itself up against the gravitational pull of the entire Earth, and winning. The electromagnetic force holding that magnet is, in a very real sense, overpowering a planet. Gravity rules cosmos. It governs stars, galaxies, and the large-scale structure of everything. But at the particle level, it is almost embarrassingly feeble compared to the other fundamental forces. The electromagnetic force is about 1,000,000 trillion times stronger. The strong nuclear force is stronger still. Why should one of nature's four forces be so incredibly weaker than the others? This is the hierarchy problem, and it has puzzled physicists for decades. One idea is that gravity spreads into extra dimensions beyond the three we can perceive, diluting itself as it goes. Another is that its true strength is hidden by physics we don't yet understand at very small distances. Without this strange weakness of gravity, the cosmos might never have formed stars and galaxies at all. The weakness of gravity is what makes the universe habitable, and we don't know why gravity is so weak. What truly happens inside a black hole? Black holes are regions where gravity is so intense that nothing, not matter, not light, not information of any kind, can escape once it crosses the event horizon. Beyond that invisible boundary, physics as we know it struggles. Einstein's equations predict that matter falling inward collapses to a singularity, a point of infinite density, where the laws of physics simply break down. But infinite density is almost certainly a sign that our equations have reached their limit, not that nature has actually produced an infinity. Something must happen at the center of a black hole. But what? A quantum core? A loop of space-time? An entirely new kind of structure? We cannot see inside. No signal can carry information past the event horizon. The heart of a black hole is the most inaccessible place in the observable universe, sealed away behind a one-way door, waiting for a theory capable of describing it. What happens to information inside a black hole? Stephen Hawking showed, in the 1970s, that black holes are not perfectly black. Quantum effects near the event horizon should cause them to slowly radiate energy to glow, very faintly, and eventually evaporate entirely over unimaginably long timescales. But if a black hole evaporates completely, what happens to all the information about everything that ever fell into it? In quantum mechanics, information is supposed to be conserved. It can be scrambled, but never truly destroyed. If black holes erase information entirely, one of the foundational principles of physics is violated. This is the black hole information paradox, and it has challenged physicists for 50 years. For 50 years, some believe the information is somehow encoded in the radiation emitted as the black hole evaporates. Others think it persists on the event horizon, inscribed in a kind of cosmic ledger. Still others wonder if our understanding of quantum mechanics itself needs to change. The paradox touches the deepest foundations of reality. Its resolution, when and if it comes, may reshape our understanding of the universe entirely. How did the first stars form? When the universe was young and dark, before galaxies, before stars, before any light but the fading glow of the Big Bang, vast clouds of hydrogen and helium drifted through the expanding cosmos. At some point, gravity pulled parts of those clouds inward. They collapsed, heated, and ignited. The first stars were born, ending hundreds of millions of years of cosmic darkness. These first stars, called population 3 stars, were likely enormous, hundreds of times the mass of our Sun, burning hot and brilliant but briefly. They lived only a few million years before detonating as supernova, seeding the universe with the first heavy elements. But we have never seen one. Population 3 stars lived and died so long ago, so quickly, that no direct evidence has survived. We search for their fingerprints in the chemistry of ancient stars. The James Webb Space Telescope may catch a glimpse of their light, but the exact process that kindled the first fire in the universe remains a mystery. How did life begin? More than 3.5 billion years ago, something happened on Earth that had never happened before, or at least, had never happened anywhere we know of. Chemistry became biology. Molecules began to copy themselves, to organize, to respond to their environment. Life began. We don't know how. The building blocks are not mysterious. Amino acids form naturally under conditions similar to early Earth. Sugars, nucleotides, fatty acids, these appear spontaneously in laboratory experiments. But assembling these ingredients into a system that truly lives, one that metabolizes, replicates and evolves, has never been achieved. Was life born in the deep ocean, near hydrothermal vents where hot mineral-rich water pours from the seafloor? Or in shallow pools on land, subject to cycles of wetting and drying, concentrated by sunlight? Did its building blocks arrive from space, carried on comets or meteorites? Each idea has evidence. None has been proven. The moment when chemistry first woke into biology remains hidden in the deep past, one of the most profound unsolved puzzles in all of science. Are we alone? Billions of stars, billions of galaxies, thousands of confirmed planets orbiting other suns, organic molecules drifting through interstellar space, liquid oceans hiding beneath the ice of distant moons. Everything we have learned about the universe suggests the ingredients for life are abundant, and yet silence. No confirmed signal from another civilization. No microbes on Mars. No alien fossils. We have listened with radio telescopes for decades and heard only the natural hum of the cosmos. Perhaps life is common but hard to detect. Perhaps it is rare, requiring conditions so specific that Earth is genuinely extraordinary. Perhaps intelligent civilizations arise frequently but destroy themselves, or fall silent, or communicate in ways we haven't learned to recognize. We don't know. The question of whether we are alone in the universe is the oldest and most profound question humans have ever asked, and as of tonight, it remains unanswered. What is consciousness? You are reading these words or hearing them and you are aware. You have an inner experience, something it feels like to be you, right now, in this moment. That experience, awareness itself, is what we call consciousness. We know it arises from the brain. We can switch it off with anesthesia, disrupt it with drugs, and watch it flicker in brain scans. But none of this explains why physical processes in the brain produce subjective experience at all. Why should neurons firing create the feeling of seeing red, or hearing music, or sensing the weight of a question? This puzzle, sometimes called the hard problem of consciousness, has resisted every approach. Some researchers believe consciousness emerges from the way information integrates across the brain. Others think it is an fundamental property of the universe, present to some degree in all matter. Still others suspect our current concepts simply aren't adequate to describe it. Consciousness is the most immediate thing in existence, you are having it right now. And yet it remains the deepest mystery in science. Why do we dream? Every night, the sleeping brain creates worlds, sometimes vivid and coherent, sometimes strange and fragmented. We move through spaces that don't exist, speak with people long gone, feel into emotions as real as anything in waking life, and then we open our eyes, and it evaporates. Why do we dream? Scientists have proposed many answers. Dreams may consolidate memories, replaying the day's events to strengthen what's worth keeping. They may regulate emotion, offering a safe space to process fear and grief. They may be the brain's way of simulating challenges, rehearsing responses. Or perhaps dreams are simply a kind of neural background noise, the brain maintaining itself during into sleep, and the stories we find in them are something our pattern-seeking minds impose after the fact. What makes dreams mysterious is their vividness, their emotional power, and the way they sometimes seem to carry meaning. Throughout human history, dreams have been treated as messages, as prophecy, as windows into the unconscious. Whether they are any of these things, science cannot yet say. How are memories stored? Your entire life is in there somewhere. Your earliest memory, your most embarrassing moment, the face of someone you love, the words of a song you haven't heard in years. All of it encoded in the soft tissue of the brain. Somehow, though exactly how remains deeply uncertain. Memories are not stored in single locations like files in a drawer. They are patterns of activity spread across vast networks of neurons. The hippocampus helps weave these patterns together. But how a particular experience gets encoded as a durable memory, and how that memory is later retrieved is still not fully understood. What we do know is that memory is surprisingly fragile and malleable. Each time a memory is recalled, it can be subtly altered before being stored again. False memories, vivid recollections of things that never happened, can be created accidentally and feel completely real. Why do some memories last a lifetime, while others fade in days? How does a smell unlock a scene from 40 years ago? Memory is the architecture of the self, and its deepest mechanics remain one of biology's most enduring mysteries. How did language begin? Language is the most powerful thing humans have ever possessed. With it we build science, law, poetry, and love. We pass knowledge across generations and imagine worlds that don't yet exist. And yet we have no idea how it began. Our closest animal relatives can communicate with sounds and gestures, but nothing approaching the grammar, abstraction, and expressive range of human language. At some point in our evolutionary past, our ancestors crossed a threshold. They began to speak, and the world changed. Some researchers believe language grew out of gesture, with words arriving later as an extension of manual signs. Others trace it to rhythm and song, ancient chanting that gradually differentiated into words. Archaeological evidence tools, art, symbols suggests minds capable of complex thought existed tens of thousands of years ago, but the sounds themselves left no record. The origin of language is lost in time. The first conversation ever held is gone. What we know is that language happened, and it transformed our species completely. How remains a beautiful mystery. Why do we need sleep? You will spend roughly 1/3 of your life asleep. That is not a small investment. In evolutionary terms, sleep seems costly. A vulnerable animal is an easy target. And yet every creature we've studied sleeps in some form. The universality of sleep suggests it is essential, but essential for what, exactly, remains uncertain. Sleep appears to be involved in memory consolidation, the brain processing and organizing the day's experiences. It may also allow the brain to clear metabolic waste that accumulates during waking hours. It regulates hormones, repairs tissue, and seems to reset emotional balance. But no single explanation accounts for all of it. Different animals sleep in wildly different ways. Dolphins sleep with only half their brain at a time. Some birds doze while flying. Some animals need very little sleep at all. What we know for certain is that without sleep, minds and bodies break down quickly. What we don't know is the full reason why. Tonight, as you drift toward it, sleep itself remains one of science's most intimate mysteries. Why do we age? Every living creature ages. The body that was once quick and resilient becomes, over time, slower and more fragile. Why? One explanation involves telomeres, the protective caps at the ends of chromosomes, that shorten with each cell division, until the cell can no longer divide at all. Another points to accumulated damage from reactive molecules, slow corrosion that builds across a lifetime. A third theory frames aging as an evolutionary trade-off. Energy that could maintain the body is prioritized for reproduction in youth, leaving decline for later. And yet nature offers exceptions that challenge every tidy explanation. Greenland sharks live for more than 400 years. Bowhead whales sail Arctic seas for 2 centuries. Naked mole rats live 10 times longer than similar rodents, with remarkable resistance to cancer and aging. Some jellyfish appear to reverse their development entirely. Why do some creatures resist aging while humans cannot? Each exception seems to have its own secret, and we don't yet know how to read any of them. What drives migration? Every year, across the planet, creatures undertake journeys of extraordinary precision. Arctic terns cross the entire globe. Monarch butterflies travel thousands of miles from Canada to a handful of mountain forests in Mexico, and their descendants return to the very same trees, generation after generation, though no single butterfly makes the full round trip. Salmon hatch in mountain streams, spend years in the open ocean, and return to the exact stream where they were born. Sea turtles crawl ashore on the very beach where they hatched, decades earlier, crossing entire oceans to find it. Scientists have found, some clues. Some animals navigate by the sun, adjusting for the time of day. Some may sense Earth's magnetic field. Some seem to use smell. But none of these explanations fully account for the precision involved. How a butterfly that has never made a journey before knows exactly where to go, how a turtle finds one patch of sand on a planet covered in oceans remains partly unexplained. Migration is one of life's oldest rhythms, and we still don't fully understand the map that guides it. What are fast radio bursts? In 2007, astronomers detected a powerful burst of radio waves lasting just a few milliseconds. It had crossed billions of light-years of space, and in that brief flash, it had released as much energy as the sun produces in an entire year. Since then, hundreds more have been detected. We call them fast radio bursts, or FRBs. Some repeat, flaring again from the same region of the sky. Others appear once and are never heard from again. What causes them? Magnetars negative, IC. Extraordinarily magnetic neutron stars are among the leading candidates for the repeating ones. Catastrophic events like the collapse of a massive star might account for the one-off bursts. But no single explanation fits them all. Every so often, the universe sends a brief, furious shout across the void. We hear it. We can measure it. We can localize its direction. But who or what is speaking remains unknown. What is mathematics? Here is a strange and beautiful puzzle. Mathematics is something humans invented, a system of symbols and logic built up carefully over centuries. And yet, when physicists write equations describing the behavior of particles, they often find that the laws of physics are not as simple as they seem. Or the curvature of spacetime, or the evolution of galaxies, they work with astonishing precision. Abstract mathematical structures dreamed up for purely theoretical reasons turn out to describe the real universe with uncanny accuracy. Einstein's field equations predicted black holes before anyone believed they could actually exist. Maxwell's equations described radio waves before radio was invented. The mathematics was there before the physics was discovered. Why should this be? Is mathematics something humans invented, or something we discovered, a language built into the structure of reality itself? Or is it a tool shaped by our minds and our evolution, adapted by chance to fit the patterns around us? No one truly knows. Mathematics sits at the center of science, describing everything we can measure. And yet what mathematics actually is, whether it exists independently of minds, whether the universe is, in some sense, made of mathematics, remains one of the deepest unsolved questions of all. Why does time feel the way it does? Time is one of the most familiar things in existence. You have lived inside it every moment of your life, and yet, it is also one of the most mysterious. Einstein showed that time is not absolute, it runs differently depending on speed and gravity. A clock at the top of a mountain ticks slightly faster than one at sea level. An astronaut ages fractionally less than someone who stayed on Earth. Time bends around mass, stretches at high speed, and flows differently in different places. And yet our subjective experience of time is stranger still. A moment of fear can feel like it lasts forever. A joyful afternoon can vanish in what feels like minutes. Childhood summers seemed endless. Adult years slip by. The same clock hour can feel like nothing or like eternity. Depending on what fills it. Why does time feel elastic? Why do we experience it as a one-way river? Why do some moments seem to stand still while others blur past? Physics gives us equations. It doesn't yet give us the full answer. Will the universe end? Everything that has a beginning may have an end. If the universe began, will it also conclude? Scientists imagine several possibilities. In one scenario, the universe expands forever, growing cooler and emptier as stars burn out and galaxies fade, until all that remains is cold darkness and the silence between dead suns. This is called heat death. In another, expansion might eventually slow and reverse, collapsing everything back into a single point, the Big Crunch, a reverse Big Bang that ends everything as it began. In a third scenario, the Big Rip, dark energy grows stronger over time, eventually tearing apart not just galaxies but atoms themselves, unraveling the very fabric of matter. Which of these awaits us? We genuinely, don't know. The future of the universe depends on the nature of dark energy, which remains a mystery. The cosmos may endure for trillions of years. Its fate is written in forces we cannot yet read. The greatest mystery of all, we have traveled tonight through 100 questions. From the origin of the universe to the mystery of a sleeping mind. From the hidden nature of time to the invisible forces stretching space. From the first star that ever ignited to the first cell that ever divided. Each one is a reminder that knowledge is not a closed book. It is an open landscape full of light in some places, and full of shadow in others. And the shadows are not something to fear. They are where the next discoveries are waiting. Science is not a collection of final answers. It is a practice of curiosity. And curiosity is what has brought you here tonight, even if you came here just to sleep. As you lie here now, let these questions drift. You don't need to solve them. No one does tonight. They have rested in the dark for millennia, and can rest a little longer. They are patient, the way stars are patient. The way the deep ocean is patient. Let your breathing slow. Let your thoughts soften at the edges. The mysteries of the cosmos are not urgent, they are vast and quiet and old, and they have existed far longer than any answer will. You are a brief, extraordinary consciousness in an enormous, mostly unknown universe. And right now, in this moment, the most scientific thing you can do is rest. May your dreams be filled with questions, and may the questions carry you gently into sleep. Good night.